Good morning. Hello and welcome. Once again, I welcome you in the lecture series of course Elements of Machine Design. We are in the chapter number 3, that is Design of Shaft, Key and Couplings. In last several lectures we have completed some examples on key and shaft. In that examples we have covered different problems of different types on the basis of given criteria. With continuation with that, today we will again go through the one example on the shaft, that is element of shaft. In previous lectures we have covered the examples of shaft on the basis of design of shaft on the basis of strength and design of shaft on the basis of rigidity, design of shaft when the shaft is subjected to simultaneous bending and twisting moment, and design of shaft when the shaft is subjected to shock and fatigue loading. In today's lecture we will cover one example on design of shaft on the basis of lateral rigidity. That is when there is a twist in the shaft or some or deflection of a shaft for certain degrees. So let's start with the example. An example is given. A steel spindle transmit 4 kilowatt. A steel spindle transmits 4 kilowatt at 800 rpm. The angular deflection should not exceed, means lateral rigidity. The angular deflection should not exceed 0.25 degree per meter of spindle. If the modulus of rigidity, the value of modulus of rigidity for the material of the spindle is 84 gigapascal, find the diameter of spindle and the shear stress induced in the spindle. So this example is based on the lateral rigidity. What is given in this example? A steel spindle is there which is transmitting 4 kilowatt, means it is transmitting a power of 4 kilowatt. When we convert this 4 kilowatt into watt, we get 4000 watt. And this power is transmitted at a speed of 800 rpm. The speed of that spindle is 800 rpm. The angular deflection, while transmitting this, the angular deflection of spindle should not exceed 0.25 degree. One criteria is given, one condition is given, that while transmitting the power, the angular deflection should not exceed 0.25 degree per meter of length, means for a 1 meter of length the deflection is allowed 0.25 degree. We have to convert this 0.25 degree into radians. The given is 0.25 degree. We have to convert this 0.25 degree into radian by multiplying it with pi by 180. So we have multiplied it with the pi by 180 and we have converted this value in radians by multiplying this degree value which is given in degree by pi by 180. So we get theta, means angular deflection in radians. The length of spindle is given 1 meter. Here it per meter of length means per meter means 1 meter. Otherwise it is specified 3 meter or 2 meter, but it is not specified. It is per meter, means length of the spindle is 1 meter. We have to convert this in mm. Then the modulus of rigidity of that metal is given, means value of capital G. We denote modulus of rigidity by a notation of capital G. That value is given as 84 gigapascal. Pascal. So once again we have to convert this gigapascal into Newton per mm square. In previous lectures we have seen the 1 megapascal is equal to 1 Newton per mm square. 1 megapascal is equal to 1 Newton per mm square, but it is a gigapascal, so it is a 10 raised to 9, means it is a Newton per meter square, 10 raised to 9 Newton per meter square. When we convert this in mm square, it will be 84 into 10 raised to 3 Newton per mm square. 84 megapascal is equal to 1 Newton per mm square. Megapascal means 10 raised to 6, but it is gigapascal is 10 raised to 9. So 10 raised to 9 minus 10 raised to 6, 10 raised to 3 Newton per mm square. Because the relationship is that 1 megapascal is equal to 1 Newton per mm square. This is the relation. So it is given in gigapascal. So we get 84 into 10 raised to 3 Newton per mm square. Now what we have to find? We have to find the diameter of the spindle and shear stress induced in that spindle. So first of all, start with the diameter of spindle. Let small d is the diameter of spindle. The first step already we have carried in lot of examples is to find out the torque transmitted by shaft, because power is given, so we have to find out the torque transmitted. Again we are using the equation of power for the to determine the torque transmitted, that is equation P is equal to 2 pi nt divided by 60. 2 pi nt divided by 60, that equation we are using, and we are determining the torque transmitted. Here we get in Newton meter, we have to convert it in Newton mm. If you use this equation, you will get this torque in Newton meter, and again we have to convert this Newton meter into Newton mm, because we are converting all units in CGS units, that is the mm. So from this we get torque transmitted. Again we have the equation for rigidity, lateral rigidity. When there is an angular deflection in the shaft, we have the equation T by J is equal to G theta by L, where T is the torque transmitted, J is the polar moment of inertia, G is the modulus of rigidity in Newton per mm square, theta is the angular deflection in radians. Keep in mind, always take this angular deflection in radians. L is the length of the shaft or spindle. So we know the value of, again we can write this equation in this term, J is equal to T into L, T into length divided by J into theta. We know the value of J, pi by 32 d raised to 4. As spindle is the circular element, so value of polar moment of inertia is pi by 32 into d raised to 4. So this is the value of polar moment of inertia is equal to T. We have already determined the value of torque. Here we have determined the value of torque in Newton mm, 47,740 Newton mm, this value. Again length is 1000 mm, we have converted this meter into mm. G is the modulus of rigidity in Newton per mm square, 84 into 10 raised to 3 Newton per mm square, and theta is the angular deflection in radians. So from this we know pi by 32 into d raised to 4 is the value of J, polar moment of inertia. So from this we get, if we solve this, we get small d is equal to 33.87 mm, that is 35 mm. So this is the value of diameter of spindle. What we have done? First we have calculated the torque transmitted, and then we have used the equation of lateral rigidity. When the shaft is subjected, design of shaft on the basis of lateral rigidity. This is the basic equation, T by J is equal to G theta by L, and from that we have determined the diameter of shaft or spindle. Now second value that we have to determine is the shear stress induced in the spindle. We denote shear stress by the value of tau. Now we know that basic equation of torque transmission. We know that the torque transmitted by the shaft or spindle is given as T is equal to, capital T is equal to pi by 16 tau dq. This is the basic equation of torque transmitted. We already determined the value of torque here. Pi by 16 constant, tau, that we have to find out. D cube, we already determined the value of diameter. So after determining the value of diameter, you can put this value here, 35 meter cube, and from this we can determine the tau in Newton per mm square. That is 5.767 Newton per mm square. So simple way, what we have done, we have just used the basic equation of torque transmitted by solid shaft, that is capital T, torque is equal to, this is the value of torque, which is we have already determined here, is equal to pi by 16 tau d cube. And from that we have determined the value of tau, already we have determined the value of d, and from this we get the shear stress induced is 5.67 Newton per mm square. So this is the example of shaft or spindle to determine the diameter of shaft and shear stress induced in the shaft on the basis of lateral rigidity, means when the shaft is subjected to or spindle is subjected to angular deflection. So here we have completed the different types on the element shaft. Now we will go through one example on coupling, because we have in theory we have seen the design procedure of flange and flexible coupling. We will cover one example on coupling. Up to this point we have covered the different examples on the shaft. Just now try to cover one example on coupling. You will going to understand how the coupling will be designed. So one example is given on a coupling, that is muff coupling. One example is given on muff coupling. Design and make a neat dimensional sketch of a muff coupling. It is a muff coupling which is used to connect two steel shafts transmitting 40 kilowatt at 350 rpm. The material for the shafts and key is plain carbon steel, for which allowable shear and crushing stresses may be taken as 40 megapascal and 80 megapascal. The material for the muff is cast iron, for which the allowable shear stress may be assumed as 15 megapascal. Now what is given? We have to design a muff coupling. Keep in mind, this example is on the muff coupling. We have to design a muff coupling. Designing of muff coupling is nothing but determining the dimensions of muff coupling or determining the stresses induced in muff coupling. That is the design procedure of muff coupling. We need to design the different dimensions of the muff coupling, the elements of the muff coupling. So what is given here? Muff coupling is there, which is connecting two shafts, which is transmitting 40 kilowatt. The power transmitted by shaft is 40 kilowatt at 350 rpm. The speed of the shaft is 350 rpm. Now there are two materials. One is shaft material and another is muff material or sleeve material, what we call, because it is a muff coupling. There are two elements. One is actually there are three elements for the muff coupling. One is muff, another is shaft, and third element is key. So there are total three elements in the muff coupling. The two materials are given. One material is given for shaft and one material is given for the muff. The material for the muff is cast iron and the material for the shaft and key is plain carbon steel. So shear stress for shaft and key is given as 40 megapascal. This is the shear stress for shaft and key. 40 megapascal, we have to convert this in Newton per mm square, which is equal to 40 Newton per mm square. because we know that 1 megapascal is equal to 1 Newton per mm square, and crushing stress is given for shaft and key, which is taken as 80 megapascal. Again we have to convert this 80 megapascal in 80 Newton per mm square. So this is regarding shaft and key. It is having the same material, so same values of shear stress and crushing stress. And another material is given, which is cast iron, which is for muff. This shear stress is given 15 megapascal is equal to 15 Newton per mm square. So there are total 3 elements: shaft, key and muff. The element of shaft and key is same, so the shear stress value and crushing stress value for shaft and key is same. The material for cast iron is different, muff is different, that is cast iron. So the value of shear stress induced in muff is 15 megapascal. Now we have to design a muff coupling, means we have to determine the dimensions of muff coupling. So first of all we will design a shaft, as there are 3 elements: shaft, muff means sleeve and key. So first we will design a shaft. We know that small d is the diameter of shaft. Again we are using the basic equation, that is the torque transmitted by the shaft. So this is the basic equation of power. From that we can determine the torque transmitted by shaft. First of all we will get this value in Newton meter, then we have to convert it in Newton mm. If you use this equation, P is equal to 2 pi nt divided by 60. This is the basic equation of power transmitted. As the power is given, from that we can determine the torque transmitted. So first step we have calculated the torque transmitted. Then again we are using the basic equation, torque transmitted by shaft, that is pi by 16 tau dq. First of all we have determined the torque transmitted by shaft by using the equation of power, because the value of power is given, RPM is given. After determining the torque transmitted from the equation of power, then we are using the basic equation of torque transmitted by shaft, that is capital T is equal to pi by 16 tau dq. Now in this case this tau is for shaft, because this torque is transmitted by shaft. So we have to use the value of tau shaft, which is given as 40 megapascal. So from this we can get the value of diameter of shaft, means the design of shaft is completed. The design of shaft is nothing but determining the diameter of shaft. So in this step we have designed the shaft, means we have determined the diameter of shaft. The next element is sleeve or muff. So next element that we have to design is muff. So first of all we are using some empirical relationships, standard formulas. We know that the outer diameter of the muff, capital D, is given as 2 times diameter of shaft plus 13 mm. Here we get the diameter of shaft. So 2 times diameter of shaft, 55 mm plus 13. So we get design of sleeve, means determining the different dimensions of sleeve, different dimensions of muff. So this is the first dimension of muff, that is outer diameter of the muff. We have designed this by using empirical relationship, basic formula. Then length of muff. Again a standard formula is there to determine the length of muff. 3.5 times diameter of shaft. Diameter of shaft is 55 mm. So length of muff is 192.5 mm or 195 mm. Or you can directly take this as it is value. There is no doubt regarding this. You can directly take these values because this is the standard diameter of shaft. So we have converted this into 125 mm. We can directly take length is equal to 193 mm also. There is no issue. Now we have determined the capital D and we have determined the length of the muff by using empirical relationships. But we need to check whether the stress induced in muff is safe or not. The stress induced in muff material, that is cast iron, that is shear stress, is safe or not. So we have to check the stress induced in MUF. Already it is given in problem, but we have to check. Let us now check the induced shear stress in the MUF. Let tau C be the induced shear stress in the MUF, which is having cast iron material, which is made up of cast iron. As the MUF is considered as a hollow shaft, therefore the torque transmitted while studying the theory part of design of MUF coupling, we know that while designing a MUF coupling, while framing the equation of MUF coupling, we have considered the MUF as a hollow shaft. So we have to use the equation of hollow shaft, that is torque transmitted by hollow shaft. So this is the equation of torque transmitted by hollow shaft. Capital T is equal to pi by 16 tau d raised to 4 minus d raised to 4 divided by d, where capital D is the outer diameter of MUF, small d is the diameter of shaft, tau C is the shear stress induced in MUF, not shaft, because we are checking the shear stress induced in MUF. So tau C, as the MUF is made up of cast iron, so we have used the small c as a suffix. Tau C that we have to find out. Already we have determined the torque transmitted here. We are using this torque transmitted pi by 16 tau C. We know the value of capital D. We know the value of small d. So from that we can get the value of shear stress induced in MUF as 2.97 Newton per mm square. Since the induced shear stress in the MUF is less than the permissible shear stress, the permissible shear stress value is given as 15 Newton per mm square. This is the value of shear stress induced in MUF, which is made up of cast iron. This value is 15 Newton per mm square, and by calculation this value comes as 2.97. So this value is less than the permissible value, so design is safe. The design of MUF is safe as this value is less than permissible value. So here we have completed the design of sleeve. Means we have determined the outer diameter of sleeve, we have determined the length of sleeve, and we have checked the shear stress induced in sleeve. Now third element is the key, because the coupling is having three elements: MUF, key and shaft. So we have designed the shaft, means we have determined the diameter of shaft. Then we have designed the MUF, means we have determined the outer diameter of MUF and length of MUF. Now we have to design the key. Now from the standard values we know that for a diameter of shaft diameter is 55 mm. We have taken the shaft diameter as 55 mm, that we have already calculated. So for a diameter of 55 mm, standard dimensions of key are: width of key is 18 mm. These values are standard. There is no need to calculate these values. You can refer this table for key, or sometimes these values are given in the example, or a chart is given in the example. So for the shaft diameter of 55 mm, the standard width of key is 18 mm. Since the crushing stress for the key material is twice the shear stress, therefore square key is used. If we observe the values for the key material, crushing stress is 40 Newton per mm square, and crushing stress is 80 megapascal, and shear stress is 40 megapascal. So in this case crushing stress is double of shear stress, and we know that for a square key, shear crushing stress for the key material is twice the shear stress. So we have used the square key. So thickness of the key will be same as width, because for the square key the width and thickness is same. तर या ठिकाणी जो क्रशिंग स्ट्रेस दिलेला आहे आणि शेअर स्ट्रेस दिलेला आहे, या दोन व्हॅल्यू जर आपण ऑब्झर्व केल्या तर क्रशिंग स्ट्रेस हा शेअर स्ट्रेसपेक्षा डबल आहे, आणि हे फक्त स्क्वेअर की साठी असतं. म्हणून या ठिकाणी आपण स्क्वेअर की यूज करू शकतो. आणि या ठिकाणी दिलेली व्हॅल्यू जी आहे शेअर स्ट्रेस आणि क्रशिंग स्ट्रेसची, यामध्ये जे रिलेशनशिप आहे ते डबल आहे. आणि आपण पाठीमागे एक डेरिव्हेशन फाइंड आउट केलेलं आहे की ज्यामध्ये आपण बघितलेलं आहे की क्रशिंग स्ट्रेसची जी व्हॅल्यू असते कीसाठी ती शेअर स्ट्रेसच्या डबल असते. म्हणजेच या ठिकाणी जो की मटेरियल यूज केलेला आहे ते आहे स्क्वेअर की, म्हणून आपण इथं स्क्वेअर की यूज करतो. आणि स्क्वेअर कीसाठी आपल्याला माहित आहे की विड्थ आणि थिकनेस हा सेम असतो. फॉर स्क्वेअर की विड्थ and thickness is same. Now the first two dimensions we have determined: thickness of की इज डिटरमाइंड, विड्थ ऑफ की इज डिटरमाइंड. आपल्याला की डिझाईन करायचं म्हणजे तिचं लेंथ, विड्थ आणि थिकनेस काढायचं आहे. म्हणजेच आपल्याला की डिझाईन करायचे आहे आणि तिच्यामध्ये जे स्ट्रेसेस इंड्यूस झालेले आहेत, शेअर स्ट्रेस आणि क्रशिंग स्ट्रेस, या दोन व्हॅल्यू चेक करायचे आहेत. म्हणजे आपण डिझाईन ऑफ की कंप्लीट करतो. नाव वी नो दॅट द लेंथ ऑफ की इज गिवन ॲज L/2. As length of muff here, this length of muff is 195 mm, so the length of key is L/2 for square key. So length of key is also given, determined. Now we have to check the stresses induced. Let us now check the induced shear and crushes stresses in the key. First of all, let us consider the shearing of the key. तर पहिल्यांदा आपण शेअर स्ट्रेस किती इंड्यूस झालेला आहे ते बघूया. वी नो दॅट द टॉर्क ट्रान्समिटेड. आपण जेव्हा डिझाईनचा थेरी पार्ट बघितला होता त्यावेळेस आपण की डिझाईन करत असताना दोन स्ट्रेसेस कन्सिडर केले होते. एक शेअर स्ट्रेस कन्सिडर केला होता आणि एक क्रशिंग स्ट्रेस कन्सिडर केला होता. मग बाय कन्सिडरिंग शेअर स्ट्रेस टॉर्क ट्रान्समिटेडचा फॉर्म्युला आपण बघितला होता and by considering crushing stress also we have seen the torque transmitted formula. So first of all, let us consider the torque transmitted by considering shearing of the key. So this is the value of capital T. We know that the torque transmitted by considering shearing of the key, capital T is equal to length of key into width, shear stress induced in key into small d by 2. So length of key is 97.5. Here we have find out that 18 is the width of key. This is the width of key. Tau that we need to find out, and small d by 2 is the diameter of shaft. So from this we get the shear stress induced 22.8 Newton per mm square, and given value of shear stress is 40 Newton per mm square. This is the given value of shear stress for key material, 40 Newton per mm square. By calculation we get 22.8 Newton per mm square. So this value is less than the permissible value. So design of key for shear stress is safe. आता या ठिकाणी जी कॅल्क्युलेशन व्हॅल्यू जी आलेली आहे डिझाईन केलेली व्हॅल्यू शेअर स्ट्रेसची, ती जी परमिसिबल व्हॅल्यू दिलेली आहे 40 न्यूटन पर mm स्क्वेअर, याच्यापेक्षा कमी आलेली आहे. दॅट्स वाय दिस इज सेफ डिझाईन. नाव वी हॅव टू चेक द क्रशिंग स्ट्रेस इन द की. अगेन वी आर युझिंग द टॉर्क ट्रान्समिटेड बाय कन्सिडरिंग क्रशिंग स्ट्रेस. Torque transmitted is equal to small l means length of key into t by 2 thickness of key, crushing stress induced in key and diameter of shaft. So length of key is 97.5. We know thickness of the key is 18 mm t by 2. We need to find out the crushing stress induced in key. This is the diameter of shaft d by 2. So from this we get the value of crushing stress induced 45.6. The given value is 80 Newton per mm square. The given value for crushing stress is 80 Newton per mm square. So calculated value is less than given value. So design of key is safe for crushing stress. So what we have done in design of coupling, first of all we have designed the shaft, means we have determined the diameter of shaft. Then we have designed the muff, means sleeve. In design of sleeve we have determined the outer diameter of muff, we have determined the length of muff, and then we have checked the shear stress induced in muff. Then in case of design of key, we have determined the width of key, we have determined the thickness of key, we have determined the length of key, because these are the three dimensions of key: width, thickness and length of key. After determining these dimensions, we have checked the shear stress induced in key and crushing stress induced in key. So this is regarding the design of coupling. How to carry out the design of coupling? Design of coupling is nothing but determining the dimensions of different elements of coupling and checking the stresses induced in that elements. I hope you have understood this problem. Here we have completed the chapter number 3. From next lecture we will start a new chapter from the syllabus. Thank you.